YOLO, Composite Gloves here, and today we're going to be solving some inclined plane problems in physics. So let me real quick show you what we got here. So we have 4 cases, and these are general cases, and all that means is we only have variables. If we had numbers, we would plug them in at the end. And it's actually kind of nice because we don't need to worry about units now. So we've got these 4 cases. They progressively get a bit harder. We're going to talk a little bit about triangles and theta and why theta appears in certain places. And we'll work our way up through these 4 problems. So the first one is the easiest. It says, and I'm going to move this. I'll move it back up if after. That way we have plenty of room to work with. An object of mass m, so I'm going to do some highlighting here. So we have an object of mass m is accelerating down a smooth ramp. So smooth means, take a note here, smooth means that our friction, our coefficient of friction mu sub k is 0. We don't have any friction, which is nice, makes it easy. Of inclination theta. So we have inclination theta, determine the object's acceleration. So that's what we want to know. So the way I always start these things off is I create a column for this column is our given column. This is the stuff we know. So for example, we know that we're on the earth. So we know gravity. We know we've got an object of mass m. So we have our mass there. We know our friction, coefficient of friction is 0. And it's mu sub k and not mu sub s because it's kinetic friction. So since we're moving, it's mu sub k. And then we also know we have inclination theta. So we're given also theta. Then we want to determine, to be determined, TBD, what our acceleration is. What is that? And now we pretty much believe we've mapped it all out. So let's go ahead. Let's make a free body diagram. So a free body diagram, right, is when you represent your object by basically a box with a dot, and then all forces originate from this dot. So first we need to draw our surface. That's pretty much the rule when you do these problems. So first we draw our surface. We know we're dealing with an inclined plane. And so there we go. There's going to be our inclined plane. We know it's 90 degrees. It's perpendicular. And we always put down our theta. So there's theta. And we're going to talk about this whole theta business here in a little bit. But we have theta. Now we always draw, our next step is draw a box with a big friggin' dot. This is where all our forces are going to come from. So first off, we know the object is in a gravitational field with some mass. So we know that we have a force of gravity, and the force of gravity is always vertically down. And I'm gonna draw this of a reasonably large size because we're going to be doing some vector. We're going to do vector. We're going to break it into vector components. I don't know why I had such a hard time saying that. But this is our force mg, right? This is just the weight. It's the mass times the acceleration due to gravity downwards. It is the weight. And we should probably identify the direction it's moving. It's accelerating down. So our object is going this way. So because it's going that way, I'm going to make that way plus. So here's plus, and then I'm going to make up this way plus. And so this brings us to our axes. We should draw some helper axes. So your x-axis should be perpendicular, or not perpendicular, it should be parallel to the ramp. So this is our x-axis, and then by definition, our y-axis is perpendicular to our x-axis. So we're going to draw those in there. Y. So whenever we deal with ramps, we always sort of tilt our axes and we resolve things relative to these axes because this is the direction our object's moving. So we want to know what's going on in this direction. We don't really care about what's going on vertically down. So we have a problem here. We have our gravity is down. It's not on our axes. So this information, we can't really use it because it's just sort of in a weird spot. Like what the heck does this even mean? So we've got to resolve this onto the components. But before we do that, we just go over here, we check our coefficient of friction is it's nothing, it's 0, so we don't need to worry about a force of friction. And our theta is already accounted for. So we can go ahead and begin to sort of resolve vectors here. So we say, well, this information's nice, but it is a little bit meaningless. So what we need to do is we need to resolve this vector. So we're going we're going to resolve it by dropping altitudes to our axis. So these are lines that are 90 degrees. That's like 30 degrees or something. It's important that it looks visually appropriate. Should at least look somewhat like 90 degrees. So there's a 90-degree angle with that line. And then this one, yeah, it's close enough. There's another 90-degree angle. It moves a little bit. It should be over here-ish. But whatever, you know. 90 degrees, 90 degrees. And so we can split it up. So we're saying that's equal to this vector and this vector. Remember, all your vectors have to originate from your big dot because this is a free body diagram. So we look at this and we say, well, this is great, but we don't know what these vectors are. So we could call this mgx and mgy because it's the vector component of the x portion. This is the vector component of the y portion. But we really want to get theta involved here because we want to have stuff that we know. We don't, this x and y thing is ambiguous. We can't evaluate that expression with this x and y. So we need to figure out where theta is. And so before I just sort of tell you where it is, I'm going to show you like the geometry here. So you remember that if we have two transversals, or not transversals, two parallel lines, and they're being intersected by a transversal, a bunch of stuff happens, right? Like for example, this angle is the same as this angle, and this angle are the same, this angle. So basically these angles are the same, right? Like this is just a brief geometry lesson. Well, let's do something here. So over here, we've got a triangle. So let's draw a triangle right now, another one. And then we've got our object, right? I'm doing like another diagram just for this little portion. Now let's pretend that our gravity vector goes all the way down. Bang, you know, just all the way down there, man. And we notice here, this triangle formed here. So here's our triangle with angle theta. Well, this would be theta minus 90, right? Because a triangle's degrees is 180. So this already takes up 90 degrees. So what's left has got to be theta, and then whatever theta is minus 90. Well, we notice here, this is also a right triangle. So this must also be theta minus 90. And this means that they are similar triangles. So we notice here, we say, hey, look at this. This angle is the same as this angle. And so we say, oh, that's an interesting discovery. That means that this angle, now I didn't draw an x-axis, but we would actually let our angles sort of extend to the x-axis. But this is a helper axis. It's not really there. We're really measuring to our triangle. So that means that this angle right here, from here to here, has got to be also theta minus 90. And if that's theta minus 90, that means that this has to be theta. So hopefully you followed that. It's a little confusing at first. I mean, I think it is. Because you're sort of looking at this. It's like everything's tilted, certainly not helping anything. But that's theta minus 90, right? And so, okay. Well, now we've got another situation. Now we've got a situation where we have this going on. Let me just draw it over here to the side. So we've now got a triangle where instead of, we have our vector coming down, but now we've got a line, our y-axis, right? So here we've got our y-axis going on, doing its y-axis thing, perpendicular basically to the surface of our triangle. And so if this is theta minus 90, and if we were to drop another line, right, and this one's parallel to our x-axis, boom, 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 boom. There we go. That's pretty parallel. This is 90 degrees as well, right? Well, we know that angles, if this is that, let me draw in one more line here, right? So this is 90 and this is theta. And so we say, okay, well, see, I just don't like, these diagrams always look a little sloppy, but hopefully you can see this is very similar to what we have going on up here. And we have this angle of 90 degrees. Well, the angle, this is going to end up being theta as well. And this is going to end up being, or this is not, yeah. That's going to end up being theta. And this is going to end up being theta minus 90. And the reason is, now we have another set of we have another transversal intersection. Because if this is theta, that means that if this were to continue upward, this would be theta. And so now we've got the parallel lines like this. We've got a parallel line going. Here's the side of our triangle. Here's the vector. And then we have our y-axis cutting it up. And we have discovered that we have this angle theta right here, because we have another line right there. All right. And so if this is theta, then that means this is theta. That means this is theta. And this one are right here. We have this and this. Let me do that in like pink or something so it's really obvious. Here's theta. So that's got to be theta. And if this is theta, that means that the other side has also got to be theta, this angle right here. And so that's also theta. So there we go. Hopefully you got that. Now this being able to prove it is like nice and stuff, but honestly, it's more useful if you just memorize it, because you don't want to do all that on a test. Like that's going to be way too crazy. So you just want to memorize that's theta and this is theta. And some people see it really fast. I sort of picture a rotating triangle, but that's the rigid proof of it. So there you go. I have like shown it to you. So now that we know these things are theta, this tells us a couple things. Well, this tells us that this is going to be, if this is theta, we can use trigonometry. So this is the opposite side. So this is going to be sine theta. And we can evaluate sine theta, like we know theta. So because we know theta, we can now tell, and we know what this is and what this is, and the mass and the acceleration due to gravity, this is now meaningful information. And this one's to the side, so this is going to be mg cosine theta. And there you have it. We have resolved our vectors, and we now have useful information to work with. And that's pretty much it. So now we come over here, and now we're going to do our equations. We've got everything sorted over there. I accidentally deleted my positive and negative, but there you go. There's our directions. That's really important. So we say, okay, we have F net. So these are our equations. Let's come over here and write down equations. And we have x equations and we have y equations. And that's because we're going to be dealing with the axes, the y direction and the x direction separately. Now, I have neglected a very important piece of this. We have a surface, which means we're going to have a normal force. And our object is said to be accelerating down the hill. It's not accelerating up or down. So our normal force has got to be equal to mg cosine theta. And it's important that it looks like it's the same size. So someone should be able to look at your diagram and basically tell what's going on. So we're going to draw one in, maybe a little bit longer. There we go. And this is our normal force. So we have x and y, and we know that we're going to have some F net x, and we're going to have some F net y. And so this just tells us what axis we're dealing with, and we have equals to. And now we ask ourselves the question about the second law of motion, Newton's second law. And we say, oh yeah, okay, so is our force balanced? Well, on the x-axis, we're accelerating downwards, so we are not balanced. So we have m1a by the second law of motion. I have a habit of putting 1 because I'm used to working with multiple masses at the same time. So sorry about that. It's kind of weird to just have like m. I'm like, whoa, throws me off. And now over here we have F net y. Are we moving up and down? No, we are balanced as is shown by our diagram. So this is equal to 0. Now we care about the acceleration. That's what we want to know. So we're going to work with the x equation. And we say, all right, well, our positive direction is defined to be going this way. So that means that mg sine is positive. So we say, well, this is going to be mg sine theta. And I like to put the little shield because it just is more readable to me, I think. But sometimes I don't put it. Is equal to ma. And we want to know a, and we can easily find a because we literally know all this info. Like we are given theta, the mass, and g. So we can just divide by the mass. And so we say mass g sine theta divided by the mass equals a. The masses cancel out, and we find out that it's just g sine theta is equal to a. And so on a smooth surface, the mass does not matter. It's kind of an interesting thing if we neglect, if friction truly is 0. So we say, okay, there we go. So that's the first one. And we're going to use this here theta thing several times. And there's actually going to be one situation where we're going to need to get a little more complicated. But you see, that is not so bad. So let's move on to the next case. So here, I'm going to move this up here. Move it right there. And let's move this one down. Boop. There we go. Just somewhere down there. Okay. So we have case 2. Now in case 2, we have a similar deal. I'm going to just go ahead and make my columns because I'm in a habit of doing this. All right, so this is going to be our given column. This is going to be our to be determined column. This is going to be our free body diagram column. These are going to be our equations. Whoa, buddy. So let's get our highlighter out. An object of mass m. So we're given m again is accelerating down a rough ramp, okay, of inclination theta. So rough ramp, that means that we're going to have a coefficient of friction. And it says with coefficient of friction mu sub k. So we are given the coefficient of friction. Granted, right now it's just sort of like it could be any number, but in this problem we would be given the coefficient of friction mu sub k. Determine its acceleration. So that's what we want to know. We say, okay, I'm on it. I'm on the job. We have a mass of m. We know we're on Earth, or all the problems are, we're just assuming that, okay? We're not like on Mars or something. And we have inclination theta. So we know theta. What else do we know? A rough ramp with coefficient of friction mu sub k. So we do have a mu sub k. Did we mark that up here? Yeah, we did. And we have acceleration. That's what we don't know. That's to be determined. So, all right, free body diagram. On it, boss. All we got to do is draw a... Let me do this in one fell swoop because my thing can recognize triangles. There we go. And we know we draw our surface first, and then we always draw a big dot in the center of a box. And this is our center of gravity, right? So, or center of mass. So we have M and G. So we should draw our forces now. So we've got mg going downwards. I'll make it a little bit big. Later on, you're going to want to be careful about how big you make your vectors. But for now, I'm going down like this. You want to make it a little bit big so you have room to work with it. So when you resolve your vectors, you're not working in such a small space. Like imagine if I had made that smaller. Like that would have been crazy bad. It would have been too tiny. So, okay, I'm going to draw my helper axis in now. So I know my x-axis has been tilted and is parallel to my surface. And my y-axis is perpendicular to that. You know, whatever. So, okay. And we should label our stuff, man. So this is mg. Oh, man. M1G, mg, whatever. And we know that we've got a new thing. So again, we're going to have to resolve our vector. And we look at the direction we're accelerating. We're accelerating down again. So because our system is moving that way, we're going to make that way positive. And I'm just going to make up positive. Sometimes people wait till they have all their stuff on their graph. But you should always make positive the direction your system's going, unless your system's like moving in different directions with the same mass. But that's like a whole different story. So, okay, we have mg. We have our theta defined, but we don't have our friction and coefficient on there. Before I put the friction and coefficient on there, I'm going to resolve mg. So I probably should write that down there so I have room. So first we need to drop altitudes to our vectors. So let's go ahead and do that. So we've got this altitude here. It should be at 90-degree angle. So it should look like a 90-degree. Like that does not look like a 90-degree angle. So I'm going to redo that one. That's okay. That's reasonably close. Even this one's a bit sketchy, but whatever. And so we know we're going to have a vector coming out this way on our y-axis and a vector coming out this way, because when we add them together, we'll wind up with this vector. So, okay, we also know from our previous discussion that we are going to have this be theta, and this is going to be theta, because this is going to be theta minus 90, making that theta, and it's going to be great. So, okay, we have theta and theta, making this mg cosine, whoops, not cosine. This is going to be sine theta. This is going to be mg cosine theta. So there's nothing new here. And then we look at our coefficient of friction, right? So we have this force. The force of friction's always opposite the direction of motion. Our direction of motion is that way. So we're going to have our coefficient of friction going this way. Now, this isn't the coefficient of friction. I've been saying that, but this isn't what it is. This is the force of friction. We don't actually know the force of friction. We only know the coefficient of friction. And the force of friction is always represented by a lowercase f with a k because we're moving. It would be an S for static if we were not moving, but it's a K for kinetic because we're moving. And if it's not lowercase f, you're wrong because that's just a symbol everyone's agreed on. Lowercase f is reserved for the force of friction. So it's literally got to be a lowercase f or it's wrong. And I think we've got just about everything on there. So, okay, let's move on over to our equations. So we do have two dimensions still. So we have an x and a y dimension. And we're going to have two forces. Now, I didn't really explain this whole F net x, F net y thing, I think, in enough detail in the first example. So F net x, when we say this, we're looking at all the net forces. So if we were to combine all our forces on the center of our object, what would we get, right? That's what this net says, is net is the sum of. So the sum of all forces in the x direction. So we got to ask ourselves, is our system balanced? And in this case, it is not. We are clearly moving down. And notice our friction vector is much smaller than our mg sine vector. And this is important. If this was somehow bigger, you would lose all your points on this problem almost. You might get credit for doing maybe this, not really. And the reason is, if this is bigger, that means we've somehow got to be moving up. And it doesn't even make sense because that's the force of friction. So this vector here must be larger because that's the direction we're accelerating. And again, I've neglected the normal force. We're not accelerating vertically, so our normal force, the force perpendicular to the surface, is going to be the same size as our mg cosine theta. So, okay, it's a little bit big. I'm going to make it a little more. It's got to be look pretty much the same. It's a horrible looking end. All right, so we are unbalanced on our x-axis. So this is, of course, going to be ma by the second law of motion. Now on the y-axis, we're not like flying up and down according to our problem. So that should be 0. And it is reflected by our normal force and our force of cosine. So there we go. We got those things squared away. Now with our information, let's go ahead and replace F net with the actual vectors it represents. So our positive direction's this way. That means that mg sine has got to be positive. If you write it the other way around, it's wrong because that's not how you defined your graph. So it's going to be mg sine theta minus f sub k equal to ma, right? And we want a, so we're going to keep working with this equation. But then we notice we don't have f sub k, but we know the definition. This is just a standard definition. So we know f sub k is equal to the coefficient of friction. It's called the coefficient because it's the number multiplied by the normal force. Whatever this is just a standard definition. And so we say, well, we don't have the normal force in this equation. So we can't continue to solve because we've got this thing we don't know. So we do know that we have it on our graph though, and it's related to our y-axis. So we come over here and we say, well, let's work with this one because it's got the coefficient of friction. So if we look over here and we say, well, positive is going this way. So that means our normal force is positive. So it's going to be our normal force minus, and so the other force on our y-axis, this is mg cosine theta. So that's going to be mg cosine theta equal to 0. So we're going to solve for n. N is equal to mg cosine theta. And so now we know f sub k is actually mu sub k, which this is given, so that's fine. But this is not given, and we just solved for it though. It's mg cosine theta. And theta is given, g is given, and m is given. So this is all good. So now we can continue to solve by going mg sine theta minus mg, mu sub k, because we're subbing in for f sub k, our force of friction. Mu sub k times mg cosine theta is equal to ma. And now we just divide by the mass, right? And we can actually factor out mg over here, right? So we get mg times sine theta minus mu sub k cosine theta equal to A, and I'm dividing by M in this same step because they cancel out, and you're left with G times sine theta minus M mu sub K, M, mu sub K cosine theta equals A. So there you go. There you have it. When we notice again, our mass cancels out. So that's kind of an interesting conclusion. We see our mass is not hanging around for these ones. Kind of an interesting deal. And so we notice, and that's when no force is being applied. So we notice we lack, besides the force of friction, we have no external force like a guy pushing our box. In that case, the mass is ignored. So it's kind of an interesting thing we notice in physics. So this is actually our answer. If we had numbers, we could plug it into this and figure out whatever the acceleration is because we've been given everything in this equation. So cool. So we're done with that one. On to the next one, right? So the next one's pretty simple after you look at the first two cases. So it does add a little bit extra though. So here we've got an object of mass m. So whoops, that's an eraser. I want a highlighter. Of mass m is pushed up a rough ramp of inclination theta with coefficient of friction mu sub k. So we're given theta, mu sub k, m, all the standard stuff from before. But now we have an applied force, and that's F sub a, capital F. So we say, oh, okay, we've got an applied force, and it is parallel to the ramp surface. Determine the acceleration up the ramp. Say, oh, this is, well, that's new. So let's go ahead, let's make our columns. We have a column here, leave some space for a diagram. So we've got given, oh my gosh, that, man, handwriting, am I right? So we have given, we have to be determined. And then over here, we've got our free body diagram. You know, I used to be really annoyed at like how much scrolling I had to do when I started taking notes on my pad. But now I'm super used to it. And then finally, we've got equations. Equations. If you're fancy, right? Am I right? Am I wrong? I don't know. So we were given the mass. We know we're on a gravitational field. We're given theta. What else are we given? We want to know the acceleration. So what's the acceleration? We're given mu sub k, all the standard stuff. And, oh yeah, we have a force now, and that force is parallel. So we have a force F sub a, and it's capital F sub a. And so we say, oh, okay, cool. And I believe that is it. Yeah, that's it. Did I spell determine right? Yeah, I spelled that right. Spelling always gets me, man. I always get a comment about some spelling error. So, okay. That aside, we need to build our ramp, right? So we boom, boom, boom. There's our ramp. And we always mark this is 90 degrees. This is theta, perpendicular ramp. Then we draw a big dot with a box in it. Boom, boom, boom. Or that didn't make any sense. A box with a big dot in it. And so all our force is going to come from this dot. And so we say, all right, well, let's do our axes first because that's like just a good first step, right? So we draw a helper axes. It kind of usually just do things in the order they occur to me because there's a lot of things happen at once. So this is Y. So we've seen all this mumbo jumbo before. So, okay, cool. Now we're given M. So we know we're going to have this gravity vector we have to resolve. Might as well do that right off the bat. So let's just go ahead, draw a perpendicular force downwards. And we know this is mg, but it's no good to us in this like random angle. Well, it's vertically down, but according to our origin on our x and y, it's like this isn't as useful. So we need to figure out a way to find out theta using it. So we do what we've been doing. We draw our, there we go. Looks sort of like 90 degrees. This is always just a little difficult. And then this one comes off at 90 degrees. There we go. And just a hint, something I found really helpful is like when you draw an arrow, your arrow is actually you actually like naturally draw lines that if you just follow the path of the arrow part right here, you'll actually wind up with a pretty good line usually. Sometimes it's dead wrong, but I found that that actually helps me draw these things. So we say, okay, cool. We've got a vector here, got a vector here. We still got to show that this is theta and that's theta. Otherwise, it's like magic. So we say mg sine theta, standard stuff now. Mg cosine theta, No big deal. We know we've got a normal force, and we know it's equal to the force in the other direction because our object's not going up and down in the y direction. It's only moving in the x direction. But we're given now we're going up. If we look here, we have an applied force parallel to the ramp surface going up. So we've got this force, maybe some guy's pushing our box here, and it is an applied force going up. And I'm making it pretty darn big. The reason I'm making it so big is that's the direction our crap's headed. So if it's not bigger than everything else, then our box likely is not headed in that direction. So we want to be visually correct as well. So now definitely clear it. We're going this way. And now, since we're on the subject, if we're going this way should be our positive direction. And I like making up positive as well, because up to me just makes sense being positive. So here we have the force F sub A going up, but we're missing something. We're missing one thing. We're missing the coefficient of friction, which is always opposite the direction of motion. So that's going this way, right? I don't know if you saw that, but I drew a blue line at the origin. And this is lowercase f sub k. Remember, it's a force of friction. It's not the coefficient, it's the force. So it's got to be lowercase f sub k. Just a friendly reminder. And then let's check. Knowing me, I may have forgotten something, and I'll bring it up when I realize in the equations, hey, where's this piece of the puzzle? But nope, we got it all. So there we go. We're good to go. Let's go over to our equations, right? We got our x and we have our y because we have 2 dimensions. We have an f net x. So this should be pretty easy. And we're moving in this direction, right? So it's going to be our mass times acceleration by the second law of motion. And then we're not moving in our y motion. So this is going to be f net y. But hopefully you've now picked up on it. We need our y equation because we have the force of friction. And the only way to really figure out the force of friction is if we use our y axis, because that has the normal force in it. So we say, okay, let's write out our f net x. We know our positive direction is this way, right? So the biggest force can be f sub a. And just a quick side note, make sure that your f sub a, your vector, is larger than your friction and your mg sine theta combined, right? Because we're not headed down, we're headed up. And it's parallel to the surface. I didn't really emphasize that, but just keep in mind, our f sub a is conveniently on the x-axis. Won't stay like that in the next problem. So we say, okay. So we have f sub a, which is our positive force as defined by our graph, minus our force of friction, minus mg sine theta. And this is equal to m sub a, or ma, not m sub a. And then we have our f net y, which we might as well define now. And that is our normal force, which is positive according to our graph, minus mg cosine theta. So this is our normal force n minus mg cosine theta. And that's equal to 0, right? Because they cancel out, because our thing isn't flying up and down on the y-axis. So let's go ahead and solve for n now, make our life easy. So we have mg cosine theta. Sweet. Later on, you get like several objects, and this xy thing becomes like just a part of what you have to do of a larger scheme. Now we have f sub a, and we actually know f sub a. Remember, that's given. That's our given column. So we say, oh, great. We don't need to worry about figuring out whatever f sub a is. And we say, because that'd be like, I don't know how you couldn't figure this out. They have to tell you. So we have our force of friction, though. And remember, note, force of friction, lowercase f sub k, is equal to mu sub k, or coefficient of friction, times the normal force. And that's just a standard definition. And so we're going to subtract, and we know it's mu sub k times our normal force, which we figured out over here. It's going to be mg, cosine theta minus mg sine theta equal to ma. And then our last step is make it easy. We just divide by m. So we have force of friction, or just our force, my bad. Just our force, applied force. I wonder, you know what? It just occurred to me, that's probably what the A stands for. I've always just kind of accepted it. But I think it's applied, our applied force. Anyways, mu sub k times mg cosine theta. Notice this time we can't factor anything out because we have our force involved here. So there's nothing in common with everything. Divide by m equals a. And we have our answer. So that's not so bad. Oh, we got a circle on that one. I guess my box was really poor. Anyways, on to the case 4, right? Last case, we got lots of room. We're going to need it because we actually have one more geometric construct I'm going to have to show you in order for you to understand. Because now we've got this new, let me show you. Let's just talk about this here. We have an object of mass m is pushed up the ramp of inclination theta. So, okay, cool. With coefficient of friction mu sub k, which is all standard stuff but this time it's a horizontal force. Ooh. This time it is a force that horizontal is horizontal. That's the way they explained it to me, meaning horizontal is always like that. Okay, even if your x-axis is defined like that, we don't care. Horizontal's like that. That's the way horizontal is. So yeah, horizontal force. So we say, ooh, exciting. And what is the object's acceleration? So less exciting. We've been asked this, 3 times before. They're trying to trick us or something. So we go, okay, let's draw our columns here. Got our given and to be determined. Sizable amount of room for our free body diagram. So we have, okay, given. Well, we know we're in a gravitational field. We're given theta. We're given the mass. What else are we given? We're given the friction, the coefficient of friction. Oh, we're given the horizontal force F sub A. So we have F sub A. And for horizontal, I wouldn't worry about that word. And then we have acceleration. I mean, we'll worry about it in the free body diagram. But don't worry about defining some alpha or something for the direction of the vector. That's what I'm saying. And then we have a to be determined. We want to know the acceleration. Again. So, okay, we draw our triangle. Boop, 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 boop. Rather sizable triangle. We mark our theta. We mark our angle, 90-degree angle. Woohoo! This is exciting. I can tell you're pretty pumped over this one because we're reaching new levels here. We draw our box here. Boom. With a dot in it. Got to have the dot. And so here we're given a couple of things. First, let's do our helper axes because on these problems, it gets to be more important. So we have our helper axes X and Y. Got that squared away. All right, so we're given that we also have this horizontal force thing. And I actually want to tackle that one first. A lot of people like to just always go at gravity first. But with the horizontal force, I just want to have it on our diagram early on so you can sort of see what's happening here. So we've got this horizontal force. So that means there's a force on this axis. And we're just going to call it horizontal line. This isn't necessary in other problems, but just to be extremely clear, it's a horizontal line. So our force is going to be along this thing. Okay? So let's go ahead and draw now. Let's do our gravity. Draw that this way. Now, in this case, these vectors can get kind of tricky. We may have to redraw some stuff, but that's no big deal. So this is mg, right? This is our weight. And let's go ahead. Let's resolve it now. So we end up with something like that, right angle. We end up with something like this, right angle. That's not quite a right angle, but it's good enough for government work. We have theta and theta. And this is no big deal. Draw our vectors. Boom, boom. And this is, of course, sine mg sine theta. Sine theta. And this is mg cosine theta. All right, now we have a vector of our force. Now our force, we should take a note real quick. What direction are we accelerating? We're accelerating up the ramp. So that means that our force, if it's going up, should probably be going this way. So I'm going to make our force rather sizable. The reason is our force has to beat friction and it has to beat mg sine theta. So our force has to be pretty big. In fact, I'm going to make it even a little bit bigger. And the reason is we're going to break it into 2 vector components. And so this can get a little bit messy. I'm going to take this mg cosine theta and I'm actually going to shrink it down because that's an advantage I can have. So there we put it right there, just this tiny little mg cosine theta. Let's resolve it. So we want to resolve it according to our x and y axes. So we're going to drop a vector to our x axes and we're going to drop a vector. I'm not going to sweat too much. So we see here we have this vector coming this way. Right there. I made it a dotted line so we could still see our mg cosine theta for our weight vector. But you see, now we're resolving all these vectors. Oh, I don't need to make this a dotted line. This can just be a straight up red line. Now we say, okay, this is great, but what angles are these? Like, how do we figure it out? Well, we know we've got a 90-degree angle here and here. And we are going to use similar geometric constructs as before. So, except for this time, we have our transversals are a bit different. So we have this horizontal line thing, right? I circled just these dots, but this horizontal line, this yellow dotted line. So there's our horizontal line. Then we also have the base of our triangle. So that's going to be, here's the base. Okay. Then we have this hypotenuse of our triangle. So here's the hypotenuse of our triangle. All right. We are given this is theta, right? If this is theta too, because this is now a transversal through two parallel lines. So that means that this is theta. All right. So that should be pretty straightforward, easy explanation. If that's theta, that means that this has to be, the 90 minus theta deal. So that's 90 degrees. Now we have a similar deal, except for now we've got our, well, this is easier to look at another way. So we notice here that we have our x-axis. I'm going to sort of write over everything in pink, but I'll erase it. We have our x-axis right here, right? If an angle goes all the way around our x-axis, that's 180 degrees, right? Well, let's take a look at what angle, because we know this angle here is theta. And if that's theta and this is theta, that means this has to be theta minus 90. So we already know that this is 90 degrees. We could even conclude that just by going, well, we could conclude that also just by going, well, these two, this is obviously the x and y, so this has to be 90 degrees. So that means that this also must be 90 degrees. And if that's 90 degrees, this is theta, making this theta minus 90. And if this is already 90 degrees down here, this thing, this also must be theta. So I was sort of some fast logic, but I don't want to get bogged down in geometry. But just so you know, this is also theta. And now we can resolve this vector. So that means that this vector right here is going to be our force. This is our force F sub A, right? So this is going to be our force F sub A y, right? And we can use trig. This is the side opposite. So it's going to be F sub A sine theta. And then this top force is going to be, this is the adjacent side, right? This side right here. So it's going to be F sub A cosine theta. And we have one last thing. And now we notice this is our cosine theta. F sub A cosine theta is much bigger than sine theta, giving us room to draw our friction force. So here's our friction force. If you were to add our friction force and our sine force together, it would definitely be smaller than our F sub A cosine theta. So we're good there. And this is our force of friction. Should label it. One more force. I'll give you 2 seconds. Quick. What's that force? Correct. It's the normal force. Now, we need to notice here, we have a cosine theta for our weight vector, and we have our FA sine theta, our applied force vector going downwards as well. So if we were to combine these together, we'd end up with something like, that big. And we're not accelerating in the y direction, right? So this also has to be of that size. So first we draw the size of our weight, and then we add on, which is actually slightly bigger. So this is a pretty big vector. So I'm not going to sweat this one too much, but this is our normal force, and it just cancels out these two added together. I think it might be a little big, but you get the idea. Let me, I'll shrink it up a little bit. Let's come over here. Something like that. What the heck? There we go. So let's just say about there. Okay. Maybe it's just a little small. Make it a bit bigger. Whatever. You get the idea. But we're still lacking something really important. If you don't put what I'm about to put on here, you get everything wrong. You don't even get graded. If this was worth 40 points, which on some of the tests I've taken it is, you would just immediately get put down to a D, which I think is a little harsh, but whatever. So our system's moving that way, right? So that's positive, and we'll make up positive. Boom. That, like, this step right here is very important. Okay, so let's go ahead and move over to our equations. Sorry, a push thumbnail came up. I was reading and talking at the same time. It's very confusing. Well, when you're reading about a whole different subject. All right, equations. We have one mass, which is really nice. So we have x equations because we have the x-axis, and we have y equations for the y-axis. And we know it's going to be f net x, and that's equal to something, and f net y, and that's equal to something. And this is ma because we're accelerating on the x-axis, but we're not accelerating on the y-axis. And we're actually going up, right? So let's go ahead and resolve the forces on the, or not resolve, let's go ahead and replace this f net with the sum of forces on the x-axis. Positive, we said, is that way. So that means that fa cosine theta has to be positive. And we're going to subtract the force of friction in mg sine theta. That's going to be equal to ma. So I actually, once you have all this junk done, I feel the math is so easy, but I'm a math tutor at the same time too. So once I get into the math realm, I'm like, oh, I'm home free now. I feel like most people are that way. So, but maybe I'm wrong. If you're in a physics course, that's what I'm saying. Usually it's like, oh. So anyways, because it's like math 150 or whatever it is, algebra 2. We have F net Y. We need that because we need our normal force for our friction. So we say, okay. Or that's going to be our normal force because that's moving in the positive direction. So that's going to be N minus, and we have two forces here. We have the FA sine theta minus our mg cosine theta, which I shrank down. It's right there. It's right here. I shrank it so we could fit in all this other stuff. Mg cosine theta. That's equal to 0. Now we have all the information we need to solve our problem. So first let's solve for n. So we know n is equal to fa sine theta plus mg cosine theta. And we remember from our note on a previous problem, mu sub k times n will give us our force of friction. So we're good there. So coming back to here, we have fa cosine theta minus, we're going to sub in this case, I'm going to put a parentheses here because we have attached by addition. So in the other cases, I just was able to sub in because it's all attached by multiplication. But in this case, we need to be a little careful. So we have mu sub k times, and mu sub k times fa sine theta minus, or plus, my bad. It's totally a plus. Fa sine theta plus mg cosine, let's see, it looks crummy. I want to fix it. Cosine theta, double parenthesis close, minus mg sine theta equal to ma. And now at this point we could do, I'm going to distribute and divide at the same time. So okay, we have fa cosine theta, and then we're going to distribute this, so this becomes minus mu sub k times fa sine theta minus mu sub k times mg cosine theta minus mg sine theta equal to, this is a all over the mass. And is there anything we can do with this? Well, we could factor out an mg and an fa by groups. And yeah, this is, you know what, this form is fine. This one's fine. We could probably find ways to make it look different, but as far as something I'd plug numbers into, this is simple enough. I could plug numbers into this and be okay with it. So anyways, we wind up with this big old thing, but that is our acceleration. And you notice as soon as we toss in another force, we get a little crazy with all this jazz. And we also notice, take note of things like this. So we notice that our mu sub k is applied to the forces going in the direction opposing our force of friction. So if you wind up with mu sub k next to things that are going in the positive direction, you probably should have a red flag go off in your head, because that should not be happening. Because we look at this, we say, well, FA sine theta is going downwards, and that was an integral part of how mu sub k affects our motion. And the other part is mg cosine theta, which is also a force headed down. So we say, okay, these two forces are related to our friction, so it makes sense. So if you ever, I don't know, I'm just trying to come up with ways to help you sort of make sense of looking at something like this. It makes sense that this force is positive because this force is a force yanking everything this way. So if we truly are accelerating up, this force being greater than all these forces put together will cause our object to accelerate that direction. So we know our equation has been set up in a way that if we're truly going up this way, our numbers should make sense with this. So there you go. 4 cases of inclined plane problems. If you have any questions about this, let me know. It's fun. They're fun. I think they're kind of fun after you sort of see it. And if anyone gave you numbers and asked you to find stuff, you could literally just turn it into one of these problems or a version of this problem, solve for your variable, and then at the end just plug in everything with the units and you have your answer. So I think they're very great ways of looking at things generally speaking. Subscribe and have a blessed day.